This presentation covers the basics of interprocess communication and introduces pipes for interprocess communication. In multiprocessing operating systems, multiple programs run simultaneously by sharing resources on the machine. The operating system context switches different processes to use the CPU, and processes that are in the ready state, that means they are ready to run, are scheduled by the operating system. Processes executing concurrently may be independent processes, that is, these are programs that are not designed to interact with each other. However, the operating system can facilitate some interactions like copy pasting, etc., between these programs, but essentially they're designed to operate as independent processes. On the other hand, several software components can be designed to operate as cooperating processes. That is, these are programs that are designed so that processes can interact with each other, exchange data and information to perform certain sophisticated operations. There are several reasons why processes want to cooperate with each other. First one, it enables building ad hoc software systems or software pipelines by interconnecting processes so as the data flows through these processes, different types of operations or processing is done on the data, thereby doing a more complex data transformation. Processes can share information, so this enables sharing data or files that one process may have loaded and it can share it with another process. It also enables processes to operate in parallel by using multiple CPUs or cores, thereby improving the performance of the task being accomplished by the collection of processes. Here, the software pipeline or the software system is constructed in a modular fashion where several loosely coupled programs are interconnected to perform different operations. This permits each program or individual piece to change independently, thereby giving a ability to develop these systems in a modular or simple way. And of course, it increases fault tolerance where errors in one process or one program is isolated to that process, and it is easy to troubleshoot smaller programs or smaller processes when compared to large complex programs. Cooperating processes use inter-process communication, that is, communication between two different processes, that is called inter-process communication, to exchange data between each other. There are two fundamental strategies for inter-process communication that is supported on almost all modern operating systems. The first one is using shared memory. This is where a portion or a small region of memory is established with the operating system as being shared, and that memory is shared between all of the cooperating processes, so there is only one physical copy of the shared memory and all of the processes read and write data to it, and that shared memory is used for accomplishing inter-process communication. The other approach is message passing. This is synonymous to working with the network. Here, processes exchange information between each other by sending small messages over the network, or sometimes it can also go through shared memory, but here the messages are explicitly sent, so there's an explicit packet of data that moves between processes. Let's look at shared memory in a little bit more detail. Here, one process creates a region of shared memory that it is willing to share between other processes. So cooperating processes then, when they start up, map the same region of shared memory into their own process space by calling system calls, so the operating system facilitates the attaching or mapping the shared memory. So when the shared memory is attached, there is only one copy of the shared memory region, and all of the processes share the single shared copy. So keep this in mind, there is only one actual shared memory region. All of the other processes, when they update their memory location, it automatically updates a single physical shared memory. So this is how the virtual memory and physical memory mappings enable the operating system to map this piece of physical memory into different processes, into the virtual memory space of different processes. So when they modify it, they all share the same memory information. Message passing, on the other hand, involves explicitly sending messages or packets of data between cooperating processes. So messages essentially contain the data to be exchanged. So all of these processes will create these messages periodically and send to each other. And the interaction between these processes is facilitated by the operating system. Keep in mind that message passing can be directly done between peer processes, or it could be sent through an intermediate server that facilitates the inter-process communication. Again, the inter-process communication through message passing can also be used with different computers that are on a network. So here packets can flow even on the network. And the idea that whether packets are flowing over the network or between operating system is usually transparent to the application program, unless the application program specifically would like to use the network for data transfer. Communication between these processes can be synchronous, that means they go in lockstep, or they can be asynchronous, where the packets are sent over the network, and whenever the packet is delivered, the receiving process processes the data. Shared memory has the advantage that it is very fast because it's directly operating with memory, and you can send and receive larger chunks of data between processes. However, coordinating these processes using shared memory can be a little bit more tricky. And of course, with shared memory, it cannot be used for communication across two computers on a network, because here you're talking about shared memory. That means processes are running on a single computer and not on multiple computers. On the other hand, message passing can be used to interact and send data between processes running on different computers. However, since it goes over the network, sometimes it can be a little bit slower, and the amount of data that you may want to pass over the network could also be limited. Now let's look at how interprocess communication and standard input-output streams are used to accomplish the process of exchanging data between processes. Assume that we have two processes. Here, of course, typically the standard error streams, or C error, where the error message is typically logged, is usually left to the console. And when we have two processes, there are two operations you can do. The first one is called redirection, where the input to a process can be redirected from a file. So rather than the user typing in data that is read through the console input or cin stream, we can redirect the data to cin, and to process one, it appears as if the user typed all of the data, but instead the operating system actually reads the data from a file and gives it as input to cin. Conversely, you can also take the output stream, console output cout, and write the outputs to a file. So rather than looking at all of the output on screen, you can simply redirect the information to a file, and it looks like as if the program generated the file. The other option you can do is also piping, which is sending the data between the two processes. Keep in mind, both the processes are simultaneously running when the piping happens. So you take the output from one process and pipe it as input to the other process. So here you're connecting two processes, and this chain can continue, and you can connect multiple processes together using pipes. Keep in mind, pipes use shared memory internally, so the pipe essentially acts as a conduit for data. And these were one of the most commonly used interprocess communication mechanisms in Unix and Linux. There are two types of pipes that Linux and Unix support. First one is called anonymous or ordinary pipes, and these pipes don't have a name associated with them, so they are anonymous, and they exist only when the communicating processes are running. And these pipes are unidirectional, so that means you can either read data or write data, in the sense that the data flows in only one direction. Keep in mind, the number of pipes you can create is always limited to the processes and the memory that is available on the machine. Named pipes are also called FIFOs, or first in, first outs. FIFOs exist independent of the communicating processes, and in Linux, these FIFOs essentially look like files, and these files on the disk essentially enable that interprocess communication, even though the data might actually be stored in a shared memory. So this named pipe, or a FIFO, exists on disk, but it's just a placeholder. Let's look at some of the common uses of redirection piping at the bash shell. Bash provides very simple and powerful mechanisms for redirection and piping. So in Bash, you can take the output of a command, in here in this case ps-fea, and you can store the output onto a file by using the greater than sign. So you can say ps-fea greater than out.txt. Here Bash then runs the ps command with that command line argument and stores the result or the output that is returned to the standard output into a file called out.txt. You can also provide input from a file. So here, assume there is some executable called myprog, and here we are giving inputs to my program from a file called testinputs.txt. So think of it as, if you want, as if you were typing the data, or think of it as copy pasting, like you could have seen the contents of testinputs.txt and copy pasted it as inputs to my program. Instead, the redirection gives you a more convenient way to give inputs to that program. Of course, you can combine the two. You can give inputs to a program by using less than, and then write the output using the greater than sign. So you could have both input and output redirection happening on a single command. Now let's look at an example of piping. Here you would use the pipe character, which is the OR character on your keyboard, same character that you use for typing an OR in C++ and Java. The same OR character is used to connect or pipe the output of one command as input to another command. In this example, we are taking the output of a command ps and piping it to the grep command. Grep here searches for a string called rawdm in the input and prints lines that match or that have the string rawdm in it. So here ps lists all of the processes, and when by piping it to grep, I'm only printing processes that have the word or the substring rawdm anywhere in a line. So this essentially accomplishes to list processes that have the word rawdm in it. Of course, pipes can be combined with redirection, so you can take different commands and you can create a software pipeline and then finally write the output to a file for future reference. Software systems or software pipelines can be easily created by interconnecting different programs together. Anonymous pipes enable interconnecting these processes where the output of one process is connected as input to another. Um, there is no upper limit on how much data they can exchange, but internally there's a finite size buffer, typically about 4 kilobytes. So data moves in blocks of 4 kilobytes between the different programs. And this movement of data enables creating ad hoc software systems or software pipelines. Let's look at some examples. So we looked at this one before, listing all processes for the user rawdm here. The ps command first generates a list, and then you pipe it to the grep command, which searches for lines which have the word rawdm and prints only those lines. Here is an example where the ls-lh command lists all of the files. Then we pipe it to another command called tr, which squeezes out multiple blank spaces. So it removes multiple blank spaces and replaces it with one. Then we are piping it to another command called cut, which cuts out columns. In this case, it is cutting out column 5 and 9, delimited by a space, and prints it as output. So there are many of these Linux commands which you can use, and you can interconnect these small Linux commands to make very sophisticated pipelines, software pipelines, to process data in different ways. Note that when you're working at these pipes, all of the processes that are participating in the software chain are running simultaneously. That is important to keep in mind. So in the last command, there are 3 processes that are simultaneously running. So ls is running, tr is running, and cut is running. And the data flows from one program to another, and it gets transformed or processed by each one of those programs. Now that we looked at anonymous pipes, let's look at named pipes or FIFOs in Linux. These FIFOs are represented as files in Linux. These files are special files, and they are created using a command called make FIFO or mkFIFO. The FIFO is represented as a file on disk, but the file name is just a placeholder because all of the data is stored in shared memory. So when you look at the size of the FIFOs, they will always be 0 even when data is stored or written to them. So there's something to keep in mind, that the FIFO on disk is just a placeholder no data is really stored in the file because all of the data is in shared memory. So let's get an example here. Let's make a FIFO called telephone. That's the name of the file. So here you're saying make a FIFO called telephone. And you can look at the file, so you will see the file. It'll appear as if it's a file on disk, but notice the letter P at the beginning of the file indicating it's a pipe. So now you can write data to that pipe. So you can, for example, output of PS command can be written to that file. And then you can print the information in that file, and you will see the information that was written by PS command into that file. Notice that here it appears that we are doing it on the same terminal, but this could be when data is written to the telephone, a completely different process or a program could have read the data. So something for you to keep a mental model there. One of the other advantages of the FIFOs is that you can also permit multiple users to read or write data to your FIFO. And this can be accomplished by managing the access permissions for the pipe that was created. So we are going to take a short look at how permissions or file permissions operate in Linux so that we can share the FIFO between multiple users on the system. Named pipes or any other files or directories are similar to files, and they all have permissions that can be used to control the users who can access information in a given file or directory. On Linux, the basic permissions are organized into three categories. There are permissions for user, that means the user who created the file or directory or a pipe entry. The group, that is a set of users that are logically belonging to the users groups. The system administrators create these groups, and each user can set up permissions for their group on each and every file or directory, thereby managing access to different people in their group. There's a third category of users called others. These are users who are not in the group or not the user who actually created the entry. These are other people on the system, and you can control access permissions to them. When you look at the access permissions in Linux, most of these permissions are displayed as letters in sets of 3 in the following form. So you will have 3 characters for the user, 3 characters for the group permissions, and 3 characters for others permissions. So you'll see these 3 characters RWX for each one of them. Where R is for read permission, that means the person can read information. W is for write permission, that means the person can write or modify the file. And X is for execute permissions, that the person will be able to run a program only if it has execute permissions. If a permission is not available in one of those categories, it's displayed as a dash. So for example, if you look at the permissions RW dash, R dash dash, and R dash dash, that means here the user, the person who created the file, has read and write permissions. The group of users that belongs to can only read the file, and others can only read the file. So that means others will not, group users and other users cannot write or execute these files. Sometimes these permissions are displayed as octal digits, where each digit corresponds to the user, group, and others. So these octal numbers, keep in mind, have 3 bits, and each one of these bits correspond to the execute privilege, the write privilege, and the read access. So the lowest bit is for the execute privilege, the middle bit is for write, and the high bit is for read. So for example, if you had these permissions RW dash, R dash dash, R dash dash, so each time you have a permission, it is encoded as a 1 bit. When a permission is missing, it's encoded as a 0 bit. So here you see the sequence of binary digits 110, 100, 100, which then maps to the octal digit 644. There's a command called change mode or change chmod that can be used to change the permissions. And of course, chmod can be used to modify the read, write, and execute permissions for the different files. And you can explicitly set permissions for the user, group, and others. So for example, let's say we want to give read, write, and execute permissions to the user to a file called test.cpp, and group and other users can read and write but not execute the file, you would use the chmod command to say user u plus rwx. That means you're adding, think of plus as adding read, write, execute permissions. And then for the others and group, you are adding rw. That means you're adding read, write with a plus sign, and subtracting or removing the execute permission. That's what the -x does. And then you can specify one or multiple files, and these permissions are applied to all of the files you have specified in that list. And instead of a file, it could be a FIFO, it could be a directory, so these commands can apply to any information that is stored on disk. Of course, you can use the octal syntax, but typically working with the user, group, and others is more explicit and consistent, and prefer that notation over the octal digit notation, although a lot of people still like to use those octal digits just because it's a little bit shorter to type 3 characters rather than type a lot of the permissions. But typing those permissions explicitly helps you understand the information that you're providing or the permissions you're setting up. Of course, here's an example where all of these are synonymous commands that set the same set of permissions, but they're just in different syntax. So you could use any one of these syntax that you find easy to remember and easy to work with. Of course, use caution with permissions. Make sure you're double checking what permissions that you set, because if you give accidentally provide too much access to some of the users, a potentially malicious user on the system can abuse your permissions. And oftentimes is a common source of cybersecurity issues on shared infrastructures. So it is important to be cautious and careful when changing permissions on files. All right, let's do a quick recap of this of the IPC mechanisms. Remember, interprocess communication is used between cooperating processes. So there are 2 or more processes that are exchanging data. There are 2 fundamental strategies. First one is shared memory. Almost all of this presentation focused on shared memory. So shared memory is predominantly used for pipes, making FIFOs. All of these typically use shared memory. Of course, you can also use message passing. This is synonymous to working on the network, sending data over the network. In the next presentation, we will look at how to programmatically create pipes, anonymous pipes in programs, and use these pipes for moving data or between processes that we'll use fork and exec to create.